So we'll look into details of variance, how it is defined, and uh, quite interesting. I spent quite a lot of time kind of figuring out what it is, uh, and we'll cover that. All right. Uh, I will share the slides with you after the class. Just remind me. Okay. Uh, for now, let's just go through them. All right. So what is a variance? So variance of a random variable x. All right, where x could be a discrete, continuous variable or any kind of variable, is its second central moment. So the first central moment is the mean, right? Uh, understand it's a random variable, and that's why you have a central moment concept. The expected value of, and it is the expected value of the square deviation from the mean. All right. So so mean, which is the expected value of the random variable itself, that's mean, right? And the variance of that random variable x is the expected value of difference between the value and the mean and squared. All right. And you can also say that variance of x, which is a random variable, is equal to the covariance of x comma x. All right. We will see why we have to do this. I mean, you can say that you can just write it as variance, but we'll look at that concept, all right, as we move ahead. So now, if I was to look at this equation, uh, just a second. Let me set the Wacom settings. Uh, 1 second. Hmm. All right. So if we look at uh, the variance equation, all right. Now what we see is that I can replace the mu with e of x, right? So variance is expected value of x minus expected value of x the whole square, right? And so the expected value of all of this, right? And now expected value follows linearity, all right, which means expected value of uh, a plus b is equal to expected value of a plus expected value of b, right? So because of that, I can say that the expected value of all of these values is nothing but x square plus expected value of x the whole square minus 2 into x into expected value of x. All right. Now let's understand what do you mean by expected value, right? Say we have uh, uh, even in the case of mu, right? First, conceptually, this should be very clear to you. What do you mean by uh, expected value uh, of x, right? So what was x? X is a random variable, right? So now let's say x has been drawn. So x is basically some sample, right? Let's say, right? So may or may not be, right? So x is some sample of size n, all right? And so let's say this x is a sample of some population. Let's call it y, all right? So now y has, let's say, total m elements, all right? And such that x belongs to y, all right? So we have y, and somewhere there is x, right? When I'm saying x, now it's a random variable, right? So when I'm saying expected value of x, what I mean is what is the average of all the values in y, right? So that will give me the actual expected value of x. Uh, say say let's say this is 10, all right, and this is 1,000 values, right? So I'm saying expected value of x actually is equal to I is equal to 1 to 1,000, all right, divided by 1,000. Is this clear? Have you understood what we are doing here? So expected value of x is actually we're saying what is it that we would expect. Actual value of what we get as x, right, of the sample will be what? So actual value of x is equal to what? Is equal to summation of xi 1 to 10, all right, 1 by 10, right? So this is the actual value of x that we of the from the sample of the random variable x, right? In some cases, your n could be equal to m, right? In which case the actual value and the expected value will become the same. So, so just want you to be clear about this concept of expected value. So expected value is not the uh, average of what of the sample size. It is the uh, it is the expected average uh, of the larger population. All right. Where is the problem? Where is the probability here or Okay, no, you can introduce the probability. Let's say the probability is 1 by n for all cases or 1 by m for all the cases, right? Let's assume that. Yeah, right. So let's assume simple for simplicity's sake, let's say equal probability, right? So probability distribution can be anything. Say we have some data points and they could have any probability distribution, but still the expected value concept will hold. In our case, we are saying the probability is 1 by, so we've taken that the probability is, uh, uh, so the probability is 1 by, let's call it some element p, all right, where p is equal to total number of elements. Is this clear? Yeah. So understand this conceptual difference between expected value and actual value. Is it very clear? Because this is the whole basis for whatever we're doing moving ahead. So not just mathematically, you should be clear about it conceptually. Have you understood this? Okay, so I'll move ahead. All right. So now coming back to my previous slide. So I'm saying now what is variance? You haven't understood this. Okay. Let me spend some time on this. Now, what is the mean of, let's not say random number, right? What is the mean of uh, your class uh, age? So each individual in the classroom, you have an age. Is that a random variable? First of all, it is not a random variable. It is actually known, right? Only if I was to take a sample out of it, then it's a random variable, right? The moment I'm talking about sampling, the randomness comes into picture. As long as I'm saying the each one, right? Everyone, the whole population set, then there is no question of randomness. That is actual data, right? So basically we call it descriptive statistics, right? We are just describing the data that is there. You got this? So it's different from inferential statistics. The whole purpose of inferential statistics is that we cannot have all the data with us, all right, and therefore we'll take a sample out of the data and we will use that sample to actually infer something about the whole data. So in your class, let's say you have say first yearites, there are 114 first yearites, let's assume, right? So 114 first yearites, when they filled up their forms in SSU, everyone has filled up their date of birth, right? Based on that, we can actually compute the actual average age of the class, right? So this is not randomness there. That is the actual mean of the data. Is this clear? Right? Here what we are saying is we are interested in the expected mean, right? So we are interested in the expected mean. Why is the question of expected? So out of those 100, if I was to pick up some 10 people randomly, what is the average age of those 10 people? It so happens that because of the concept of randomness, all right, and the independence involved, the expected value would tend to be equal to the actual value, right? As the sample size becomes sufficiently large enough, but there is still a gap. Have you understood? So there is something which is still missing. It is not exactly accurate. So how accurate is it, or how inaccurate is it? How inaccurate is that, uh, uh, or how much of the error is there in that measurement of mean? Have you understood what is my next question? First, the error is there, right? So what I'm saying is, for example, look at this, right? Summation of I is equal to 1 to 1000. This is the actual. So this is what I expect, right? So, so expected is this. Let me call it mu. All right. Now, how do I can't compute this? I only have 10 values, right? So I actually compute this, right? But what I'm saying is, this is the actual computation. So this is x. So this is not expected value of x. Understand? This is x. I'm saying my expected value of should be this, which is nothing but mu, right? So this is my x. Sorry, this is my, let's call it actual value of average of x, right? So this is actual value of average of x is this, right? Now I'm saying that this average of x, let me denote it by uh, something called a, right? A of x, right? A of x is summation of xi by 10, right? 1 to 10, all right? Now I'm saying that expected value of this ax, what is that? And that we have seen earlier also would be equal to mu, because we're saying that we expect that that is what the randomness concept would give me when I pull out the 10 data points, right? So this expected value is mu and not this actual value. So now this is the concept. So but actually in reality what will happen is we only have ax, right? So we have ax, that is what we can compute, all right? And then we have mu. It We may be able to compute it, we may not be able to. So this is very important. We may or may not be able to compute this. All right. So mu is another value that I have. I'm saying what is going to be the difference between the two? How much of the error is involved there? That is where the concept of variance comes. Wherein I say, okay, if I was to take, so I took one sample, right? So if I was to take such 5 samples, right? So each of these 5 samples will give me some average value A1, A2, A3, A4, A5. Now each of them have expected value of mu, right? So each of them is expected value is mu. But in reality, this is not the value that has come out, right? So these values follow a distribution curve with some probability. Is this clear? So these values follow some distribution curve with a probability. Now, what is that distribution curve? How do I compute that? So basically I need two parameters, right? Typically, one is the mean and another is the standard deviation, right? So if I take the standard, uh, so if I was to compute the uh, standard deviation of this, that would somehow give me some idea about the actual possibility of the error. So is it conceptually kind of clear to you? Don't drop the mathematics. All I'm saying is, uh, say when you take the sample may not is not really going to give you the exact answer, right? So, but at least what I want to know is how accurate is my sample? How close is my sample to the actual answer without knowing the actual answer? Is this fine? You got this concept? That is what I'm interested in, and that is where the concept of variance comes in. Okay, so let's come back to Chandramouli says it is what I get expect in the exam and what I actually get. No, if you were to expect in the exam, then you would expect average marks. That's 50%, right? You expect 90%, and then you get maybe 60%. So there's a bias there. So right. So because expectation is always an average. All right. So what you wish and what you actually get is the question of examination, but what you expect from a population is always the average, not the best, right? So I'm saying, okay, if I was to so this is interesting, right? So in the exam you expect most maximum marks based on your preparation, right? It is not the average of whatever you prepared. Are you getting the difference? So that expectation is different from the expectation of choosing data from a biased, from an unbiased, with an unbiased mindset. Why is expectation an average? Because when I say I could keep on repeating, okay, uh, right. So no. Even the important questions, I'll come to your Chandramoli's example, all right? So now, why is expectation an average? Because uh, let's say a simple case of rolling a die, right? So before I have rolled the die, what value do I expect? The value which has probably given me the most probability, right? Something like that. So 1 by 6 is the probability, right? So I'll expect a value of either 3 or 4, right? Because they have the highest probability. And if I was to say I keep on rolling the die for 100 times, which is the average value that I'll get, right? Overall, if I was to take the average, I'll get something like 3.5. So that is the expected value. It converges to that. The more the dice you roll, the more the value will become like that. Let me show you. What we will do is understood, right? What if the probability is not uniform? Will it still be an average? Right. So how do you even compute the average? You compute the average using the probability, right? Isn't it? So it doesn't matter what the probability is. It is the average of those values. Correct? So if I have an unfair die, like we had discussed the last time, wherein we say, okay, the die is heavily loaded, in which case the average value was coming out to be something like 4.3 instead of 3.5, right? So I keep on rolling the die thousands of times. Overall, the average would end up being 4.3. Is this clear, Lavita? So the probability distribution does not have anything to do with the average. The probability distribution only changes the value of average. Okay, clear? All right, right. So we're saying, so okay, now General Molly's question was, let me try to see if we can fit that. He's saying, okay, we have uh, so we have last 10 years question papers, right? So out of that, you say categorize those questions into different uh, portions, saying this question belongs to this portion, this question belongs to this portion, and then you say, okay, this portion has always come, a question like this has always come, so you're drawing the probability curve of that, right? So you're saying, okay, overall 100 questions, out of that how many have got repeated, so you actually get a probability curve of all the questions. And then, so after that, so now what you're doing is you are kind of seeing that those which have the highest probability tend to be closer to the average, but at the same time it need not be. All right, so Chandramouli, here the trick is this: we do not know what is the distribution curve. It could be such that let me add another. So let's say this is my distribution curve for the questions that are asked, right? Let's say normal, right? So this is some uh, and I assign based on the frequency, maybe the I will have to convert the questions into a random variable first, right? So doesn't matter, let it be not even right skewed or left skewed, whatever it is, right? So I will get some. So which are the ones that I would expect most? I would expect those most which have had shown the highest probability, right? So those are the questions that I would expect most, right? And very truly, these questions would very closely also, they are close to the average, right? So there will be some kind of an average that we can, if you were to kind of assign a number to each of the questions, right? Saying that, okay, this is the uh, weightage kind of a thing, right? It would be very difficult because actually you are saying that you can't really, convert it into a random. How do you convert it? Say, uh, for example, it is equivalent to saying, okay, I have a die, all right? So now the die normally has numbers. Instead of numbers, if I have colors, I say red here, green, blue, orange, right? Or whatever. So now I can assign numbers to this. I can say 1 is equal to 2 is equal to 3 is equal to 4 and the other two numbers, right? Say black is equal to 5. Now here my outcome was red, green, orange, blue, etc. And I have assigned a number to them. In the case of an important question paper, I would have these questions here, right? With some probability. Let's think, let me make it as question 1, question 2, question 3, like that, right? So a die which is, let's say, uh, such that there are maybe 100 sides to the die, right? An imaginary die, and each side represents some question, right? So whether the question has come or not, or when once you throw the die, five sides will be facing you, right? So those 5 sides are what the 5 questions are. Now I can assign a number to them: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And then I can kind of uh, draw the, based on those numbers, which will go typically on your x-axis, okay? I will draw probability mass function, right? So I'll draw a probability mass function, right? And this probability mass function now gives me an average. But the whole problem is, understand this, that because I've converted into numeric, which is what I need to do, right? I've converted it into numeric, I would get a average which is based on these numbers. Let's say there is one number which is 100, right? And 100, the question that is at number 100 is coming only once out of 10,000, out of 1,000 times. But because this is 100 into 1 by 1,000, that's the 10,000, right? That's the probability, right? So this comes to 0.1. So it is contributing to 0.1 value, very large value, because this value is large. So we will have to do some other trick to solve this, right? So but yeah, the point is, yes, you kind of got it right. Wherein I can, so basically understand that any real situation will not have all this randomness very easily defined. Say for example, we could take this only as a case study. Say if we have questions that are coming, right? Which questions would come by what probability, right? So those things we can kind of measure, right? Or what is the expected value of the question paper? What is the expectation out of the question paper? I should be able to calculate that based on what is most likely average, right? Combination of different things which will make that average. Got it? Okay. So moving ahead. So now coming back to, so I'm saying what is my variance? My variance is about expected value of x minus mu the whole square, right? Which is basically nothing but, so what I'm saying is, let me, so come back to the original question, right? So I had uh, uh, so I had yi where I is from 1 to 1000, right? And so this is my population, right? And so I ranges from 1 to 10,000, 1 to 1000, right? And then I'm taking x out of it. Let me call it xj, all right, where j ranges from 1 to 10, all right? So now I'm taking this xj multiple times, right? So let me call it x1. So I'm saying x1j is equal to x1j, where j is equal to 1 to 10. Similarly, x2, I can say x2j, where j is equal to 1 to 10. and so on, right? X3. So each what are these 10 basically I've picked up randomly from this, right? From this 1000 set. Now, if I picked out of from a set of 1000, how many random possible ways are there of picking 10 values from a set of 1000 values? Let me call it C, right? So my combinations. How much will that be? Let's assume two ways, right? Yeah, 10 C, 1000 T10 C10, assuming I don't do any replacement, right? Uh, so many times what happens is in the case of the measurement of variance, etc., or the when we take the sample data, we are saying that we are making the assumption that I'm making replacement also, right? Because see, normally what we'll do is we'll pick up random value, right? So a random value could be generated again as well, right? So for example, throwing the die, right? So I'm throwing the die, I'm getting 1 to 6. Again, next time I'm throwing the die, I'm getting 1 to 6. So I'm replacing my set of values. So if I was to replace my set of values, in which case it will be straight away 10,000 into 10, right? So these are the possible ways that I different. Is this right? In case I'm not replacing, then C would be equal to 1000 C10. Is this clear? So either I have C, which is this, or this. This is with replacement, not with this replacement, not. Yeah, is it clear? So I have these many combinations, right? So what is the so I remember we saw the example wherein we say our sample size was 10, overall size, population size was 10, and the sample size was 2. And then we took all possible ways of selecting from those sample sizes. So we took all the samples and then we took the average of whatever the average the sample was giving, and it came out to be exactly the average as that of the overall population. Do you remember that example that we had taken? Right. So same thing I'm repeating here. So I'm saying, okay, now so I have this, right? So then I'm saying my uh, uh, my expected value of x, first of all, right? Just the expected value of x. What would that be? That would be, let's assume this case wherein I made the replacements, right? So I made all the replacements, okay, and then I'm selecting those 10 values. My expected value would be the as such it should be equal to what? It should be nothing but summation of I is 1 to 1000 yi, right, divided by 10,000. But how can I compute it from my, I should exactly get the same answer uh, uh, from my samples, right? So I only have the samples, and so how many samples am I taking? I'm taking 10,000 samples, right? And for each of the samples, what I'm doing is I'm computing the average of that sample, right? So which I call as uh, x, capital Xi, right? So this is the average of my sample, all right? Or let me say A of I, right? So A of I belongs to, let me use a better notation, makes it more clear. Uh, Let me call it X mean, all right? And then X mean of I, right? So ith sample, let's call it ith sample. So I'm taking the ith sample and I'm taking the mean, all right? And if I was to sum this ith sample all the way from 1 to C, right? I will have that many, and then divided by C, I would get the same answer. Is this clear? So here C is 10,000. So I'm taking the sample means and I divided it. This should be actually equal. There is no such thing as approximation or anything. All the possible cases. Have you understood this part? This is something we had seen last time with a small example, right? But what happens in reality? We don't have the bandwidth to take 10,000 samples, right? Or I mean 10,000 times we can't take the sample. So what we will do is we will take typically in reality we will take only one sample actually, right? What we will do is so now what should happen is that one sample should be able to convey everything about the actual population, if everything of interest to me. Are you getting what I'm saying? So we can't be retaking the samples again and again. So theoretically we can do this, but practically this is not going to happen. So then how do I solve this problem? Right? So I'm saying, okay, whatever sample I had taken, what is the distribution of the mean that sample will give, right? So this is the concept that I want to compute. Is this clear? So variance will help me to do this. Okay. So variance is basically what? Variance is how, if I was to plot this xi mean, right? So I had xi mean 10,000 times. I was to plot this, okay, as a frequency curve. What would that be? How would that values be? That is what is going to be my variance. Is this clear? Have you understood what is variance conceptually? So I have these 10,000 values of xi mean, and I plot that up, okay, as a frequency curve. What will it look like? Correct? This is very important because this concept should be clear uh, fundamentally, not mathematically. Of course, mathematics will help you to understand it, but you should be clear about it conceptually. Okay, Chandramauli got it. What about Sarvani and Lavita and Supreet? Okay, Sarvani, Lavita and Supreet. Okay, what about Lavita? Supreet also got it. I spent almost the whole day yesterday to kind of figure this out. I mean, mathematically it's always very clear, but I really wanted to understand it conceptually, and once it became clear, it was so amazing. So now Lavita is saying, but shouldn't variance be the difference between the y is calculated and the individual samples plotted? No, you will not plot the individual sample. Why are you taking the sample first of all? To actually compute some right? Statistic. You're not interested in those individual values more than, other than maybe either taking an average of that or taking some other uh, statistic out of it, right? Remember the first day, what we are interested is in a statistic. We are not interested in the sample. The sample is only doing this much, that it is giving me a, a an accurate statistic. All right, so I apply some mathematics on the sample to give me the accurate statistic. All right, so what I'm interested in is actually the mean here. My whole focus was the mean, to actually compute the mean. So I took the samples and then I take the means of each of those samples. Let's say, let's say I repeated my experiment 10,000 times, right? So I took the mean of each of these values, and these means now, when I plot them, right? So only one, say if you have just only one set of values, right? Say if I say, now what will happen? Uh, so now I'm getting x mean, right? So we'll have a lot of values, right? What I do is I do binning, right? So I create bins, let's say, right? So I say value between this and this and this and this, and here a count. I do a bin and I do a count. So based on that, I keep on, let's say, if I was to just do it manually, normally how do we do it? We say 1, 2, 3, 4, 5. Then so if it's one here, one goes here, 1, 2, 3, 5. Like that, we keep on counting. And then we plot it. This becomes our histogram, right? And typically this histogram will be something like this. So the variance is basically this graph that I'm interested in, which is for the mean, not, I mean, how much of the uh, uh, actual mean uh, of the sample differ from the the actual mean of the population. Now the thing is, If I was to just take the difference, what will happen? It will add up and the positive and the negative will cancel out and you will be left with a zero, right? So what's a better way? I kind of knock off the zero. So I want to take the distance. So what I'll do is I square it up. I could have also, uh, let's just look at it conceptually. Conceptually, I could have just taken the absolute value. I could have said this is my xi mean, all right, and then subtract it from actual value. Let's call it mu, right? And then take a mod of this, all right, and divide this whole thing by the total number of samples that I take. Okay. All right. So this will give me a better idea of how close all my values are to the actual value, all the values of the sample values are to the actual value, or how far they are, right? But okay, I'll come to each of these steps. I think as I move ahead, a lot of the things will become clear. First of all, actual mean will not have a graph. Population data can have a graph because actual mean is one value, and the thing is either it is known or unknown. Sometimes you can't even know it. It's like I want to find out the average height of people on the planet. Now this is actually there is a value existing, but I can't find it out unless I have the data of all the 7 billion people. Are you getting this? So that is the actual value of the population, all right? But I can't say this is the actual value, right? What I can do then is I can take samples out of that population. Based on those samples, I can say that with this much surety, with this much confidence level, I can say that my answer is this much accurate. But at the same time, there is 10% probability that the answer will be so far away from the actual answer, and so on. Yes, everyone, let's say, right? So I'm saying average height of the people on the planet today, right, is irrespective of their age, right? I'm saying I want to compute two things. I want to compute the average age and the average height, let's say. So it doesn't matter, no, whatever the age, everyone has a height. Is this clear? Understand the concept here, that value is not known to us. Okay, so that is where I use statistics. I say, okay, I take a sample, and then with what confidence level the sample is conveying something. We will look at maybe the random number examples, and that will probably make it more clear. All right. But so have you understood, Lavita? So there will be no graph of the actual data many a times. Okay. So now, so this is what I'm interested in. But normally, what I'll do, so this is not what I'll take, because the tradition has been, I don't know why, is actually to take xi mean minus mu the square, and then I divide it by total number of sample. No, so that will give me the expected value, right? Of that will give me the variance. But so xi mean, how do I compute that? Uh, Sorry. Uh, Yeah, so right. So xi mean total number of samples, right? So my xi mean is varying. So let's come back to this mean as a concept now, right? So I will not use the word mean every time. I would just consider it as a uh, uh, this itself, say xi mean is some uh, uh, vector. Let's call it xi dash, right? So I'm interested in this xi dash, all right? So I can straight away say that what I'm interested in is xi square minus mu xi minus mu, sorry, xi minus mu square divided by n. All right, so where n is the number of samples, let's say. So this is what I'm interested in. Okay, so coming back to our first page. All right, so this is what I'm saying. So my variance is the expected value of x minus mu the whole square. All right, and then I can expand it. Expectation is linear, which means if I say expected value, or let me just show it to you in Google on Wikipedia. Okay, so So what are the properties? The expected value of a constant is equal to the constant itself, right? We know this. So so if x and y are random variables such that x is less than equal to y, then expected value of x will always be less than equal to expected value of y, right? Linearity. So we know this. So x plus c is the expected value of x plus c, because c expected value of c is equal to c, right? Expected value of x plus y is equal to expected value of x plus expected value of y, and similarly this, right? So is this clear? So now this, he's saying that this result is valid even if it is not statistically independent of y. Combining the results from previous three equations, we can see that expected value of a of x plus b of y plus c is equal to this. All right. So they need not even be independent. Okay. The one concept of independence comes in here, wherein I say expected value of x into y, it will become expected value of x into expected value of y, provided that x and y are independent of each other. All right. So this is what is the linearity and other properties of expectation. All right. So why the square? Because square. Okay. So Lavita said, why do you need to take the square? Because by taking the square, I'm eliminating the positive or the negative, the sign there, right? Either I should have taken the absolute value, or I can take the square. I have no idea why it this whole statistics has progressed in such a way that variance is what is considered rather than absolute value. Okay. uh, but even taking the square does the same thing, right? So if I'm taking just the summation, right? If I was to just take the sum will end up becoming zero, so I can't make out the difference, right? So if there is somebody who's taller than me, somebody who's shorter than me, take the average. How far are they from the average? If I was to just take the difference, I would get zero. If I take the absolute value, I get some answer for sure, which is positive. On the other hand, if I take a square of the difference, then also I get a positive number. That is the reason why I have taken square. All right. Okay. So now, yeah. So basically, it gives me an idea about how variable how spread out the distribution is. Okay. So is the data more homogeneous or heterogeneous, right? So all right. So now basically what happens is, if I come back to my equation here, so this is what it is. So if I expand it, right, so it becomes expected value of x minus expected value of x the whole square. Then this thing I can write it as x square plus expected value of x the whole square minus 2 into expected value of 2x into expected value of x, right? Now this e, so I'm using the linearity here. What will happen is, if I use the linearity, this will become expected value of x square plus expected value of, so now 2 times the expectation will not make any difference, right? So this is straight away nothing but expected value. So this is the expected value of x square plus expected value of x the whole square, right? Because once you have an expected value, that's one constant, right? So that constant, further expectation of that constant is anyways the constant. We have already seen this, right, in the properties concept, right? So expected value of capital X will give me some value constant, right? Further expected value of that will anyways be a constant. So I can just, instead of that, I can just say expected value of x and the whole square plus minus 2 into x into expected value of x. Now expected value of x will be some constant, right? So overall the expected value of 2 into x into expected value of x will give me what? So I can replace this. So it will become 2 into expected value of x into expected value of x, right? So it will become minus 2 into expected value of x the whole square, and we already have one term here, so this gets cancelled out. So basically what are we left with? We are left with this. We get, so basically variance is nothing but expected value of x square minus expected value of x the whole square. So it is mean of square minus sum of square of mean. So is this clear? Mathematically, this concept is clear. What is variance? Expected value of x square minus square of expected value. Okay. Shall I expand this and solve it for you? Uh, we said, uh, what are we interested in? We are interested in the expected value of, need the square brackets here, x minus mu the whole square, right? Now I can expand this. This becomes, so I'm just focusing on this right now. All right. Let me call it a. So this is x square, right? Plus mu square minus 2 into mu into x. But now x is a random variable. And how did we get mu? We already knew that we have said that mu is expected value of x divided by n. We have done it in the previous class. Let's assume for now, right? So know that n is the sample size, okay, and not the population size, okay. So now what I do is, sorry, no, I don't need to divide it by n. It's just the expected value of x, right? So it's the expected value of x, all right. So what I'm saying is now this is equal to, so a is equal to, let me just make a slight change. Uh, let me call this a. So my a equals this, okay. So now my a is equal to this. Now expected value of a, expected value of a is equal to, we said linearity, right? So I can say expected value of x square, right, plus expected value of, I can replace mu square with this, wherein I can say it is expected value of x square, all right. Then I say minus 2 into uh, expected value of 2 into mu into x, right? For now, let me keep it this way only. So I can write this as expected value of x square plus, now since know that once I have an expected value here, right? So this will become a constant. Let's say in this case it is mu, say it has become a constant c, right? So now once it has become a c, right? And then you take a square of that, that's another constant, right? Expected value of a constant is the constant itself. So what will I get? So I can replace it with either a c or a mu, or just as it is, I can say expected value of x the whole square. Is this clear? So this expected value of expected value doesn't make sense, or rather it just leads to a constant value. Minus, now here these two are constants, 2 mu, right? So 2 mu into expected value of x, right? So or rather I should have expanded it later. So which will become what? Nothing but 2 into expected value of x the whole square. Is this clear now? And this is nothing but my final answer here. So I say it's the mean of square minus square of mean. Or you can say the other way, the expected value of the square minus the square of the expected value. Correct? So this should be clear to you. Okay, Sarvanit is clear to you. What about the others? Lavita? Supreet? Chandramali? Okay. Uh, Ravita, little confused? Okay, Chandramouli, it is clear. Lavita, I haven't. Okay, is it clear then, Lavita? Not clear? I think maybe if you just refer to a little bit of the math. Okay, clear. Good. All right. Excellent. So let's move ahead now, right? So now, let's look at discrete random variables, right? So now say x is a discrete random variable, probability xi. So for each of the value of xi, the probability is pi, right? Okay, such that I is equal to 1 to n, right? So then the variance of x would be given by what? It's nothing but probability of pi into, so the probability into xi minus mu, the whole square, right? I is equal to 1 to n. Okay, so this is what I get as the answer, or rather, is this clear? Huh? So simple maths here. So which I can replace by this. I can say is equal to nothing but one probability of, so pi into xi square minus mu square, right? Why so? How come it becomes like this? Basically, what happens is, same concept as we had earlier. Basically, it will be this plus, so whatever we did earlier, right? It will become plus mu square minus 2 into mu into xi summation. That becomes nothing but mu square. Is this fine? This, so there is nothing but what we had done earlier, getting into that mathematical part of it. Okay. So now when probability is pi is equal to 1 by n for all I, then what happens? The variance becomes nothing but 1 upon n xi minus mu the whole square. Okay, so that is what we started off with. Okay, and yeah, right. So this is what we get. We have, I can also write it as, so now variance is also equal to variance of x, is we said is equal to covariance of x comma x, or I can say that this is what it is actually, xi minus xj the whole square. All right, you can do this mathematically actually, right? The computation will come out to be the same, wherein if you replace mu by 1 by n upon summation of xi, right? So you expand mu and then it will come out to be this, but this is for probability of equal probability for all values, right? So I say it is, this will come out to be this. All right, just another notation, not of much relevance here. Okay, let's move ahead. So now basic properties of variance, one is that the variance of x will always be greater than or equal to 0. Why? Because it's a square, right? And then the variance of a constant random variable is 0. Okay, so if you have one constant random variable, the variance is 0, right? Because there is nothing else to compare it with. There's only one. So only when there is more than one can you say there is a variance. Is this clear? And if the variance of a variable in a data set is 0, then all the entries will have the same value. So if one, so if I have a data set of 10 values, right? If I only pick up one, the variance will be 0 because there's only one. And similarly, if I pick any other instead of that one, right? Still the variance will be the same. So what happens is if the probability that x is equal to a is given to be 1, right? So that, okay, this is going to be the value, then very clearly the probability, the variance of x will be 0. Okay, this is again just some principle that you need to remember, property of variance. Now another thing, variance is invariant with respect to changes in location parameter. What does that mean? So if I say variance of x plus a, that is nothing but equal to the variance of x. All right, so it doesn't matter if I kind of change my difference. All right, the answer will still come out to be the same. All right, where a is a constant. Okay, so if all the values are scaled by a constant, then the variance is also scaled by the square of the constant. So if I say variance of a into x, so this will become a into variance of x, a square into variance of x. Is this fine? Because if I'm scaling every value by x, what will happen? We saw that there's a concept of square, right? So that square will actually end up increasing the values also by that much factor. All right. So going ahead, we can say variance of a into x plus b into y is nothing but a square into variance of x plus b square into variance of y plus 2ab into covariance of x comma y. So there is no such concept as variance of x comma y. Variance is always typically with some between something which is totally independent, right? So x and y can have dependence also, right? So therefore I said covariance of x comma y, right? So and if we look at generality, right? So now I'm saying variance of uh, right. So covariance will cover both. Covariance of x comma y will take care of independent part also. So it is the superset in a way. We will look at that as we move ahead, right? Uh, so now, so I'm saying in general, what I'm saying variance of say xa plus, so x plus y plus z plus so on so. What is that, right? It is nothing but, so in generality case, it is nothing but covariance of xi comma xj, where I ranges from 1 to n, j also ranges from 1 to n. Okay, so basically you'll get all the possible combinations, and I can split it. I can say this is nothing but variance of xi for I is equal to 1 to n plus covariance of x comma xj where I not equal to j. So how many combinations this summation will have, by the way? This summation will have how many combinations? Tell me. There's a summation here, right? What is the summation notation conveying? How many summations will be there? N? No, this will be actually n into n. I'm just using the notation like that. I could have actually said it is equal to, a better way would have been this, wherein I put another summation here. N square it will be, right? So I could have put another one here, all right? And then I could have said I is equal to 1 to n, all right? So this is n by n. So I expand it. I say pull out those where I is equal to so is equal to j, right? So and so how many will be that? N. So I take this out, and the remaining n square minus n will come here. Is this fine? Where I is not equal to j. All right. So for example, in case of 2, right? So we had two variables a and b. So if I have a and b, right? So two variables will give me 4, right? So out of that 4, this is one, this is another, and these two combine together to form 2, right? So that many summations were happening. So and so on. Is this clear? So now, and I can write this, so this becomes variance, this becomes the covariance part. Now what happens is, similarly, I can, more generalities, I can add some constants to it. So for each of these xi samples, I say, okay, there's a constant which is a1, ai, right? So this will become nothing but ai into aj into covariance of xi comma xj. So I should actually add another one here, all right? So this is what, so I can split this same thing. I can say it is equal to a1 ai square and so on, right? So just a little bit of maths here, nothing but basically just understand the concept that this is the so variance. These are the formula that you need to remember, all right? Or maybe this one at the max. So now what happens is, if so, normally whenever we are talking about variance and everything, we're talking about random variables, right? So my x1 to xn, each of these are independent of each other if they are say uncorrelated. So one sample, when I take one sample, right, and I take another sample, the other sample will also be from the same population, and let's say it is with replacement, then the new sample has no dependence on the old sample, right? They are independent. If they're independent, the covariance between them will be 0, right? So then, so if that is the case, the variance of sum is equal to the sum of variances, all right? So we can just come back to this here. So variance of sum is equal to sum of variances. This will go off. This portion will not hold. Okay. Let me not use x here. Let me use sum. So this will knock off. All right. This portion. So only this will be left. All right. All right. So now, so this implies that variance of x is equal to, or variance of x bar, the average, right? That's what we were interested in. So variance of x bar moving ahead. So if what I'm doing now is just look at this. So if I substitute, I got this concept formula for variance. We say variance of summation of xi from 1 to n is equal to 1 to n variance of xi. Is this fine? So if I now, what I do is I imply it, I use it for sampling. All right. All this is till here it is mathematics. Okay. Now I'm coming to sampling. In my sampling case, I've taken one sample, right? And that sample has xi value, n values, right? And so variance of the average of this, right, is nothing but variance of 1 by n into, I can split it up, make it large, and then I apply my concept here, right? The one that I had earlier of taking out the constant. So I take out this constant, 1 by n square will be, right? And this becomes summation of 1 to n variance of xi, right? And now we know that the variance of xi, what is xi? Xi is one element out of that whole random population, right? Now it could be uh, any element, right? So so what is the, so that will be equal to the so now what will this be, right? So let's look at this, let's expand this. So variance of xi, right, expected value of this, let's look at the expected value of this. So expectation of this would be sigma square, which is the, what is sigma? Let me just explain. Let's assume that my population has mu and sigma, where mu is the mean and sigma is the standard deviation. All right. So expected, so I can't directly say this is what it is. Okay. So variance of this will be equal to variance of xi. All right. Now variance of xi here is from 1 to n. So this will expand and become 1 by n square. All right. If I take the expected value of this, all right. So if I take the expected value of this, I can say, so expected value of the variance, I say 1 by n square. All right. Expected value of summation. Okay. So I'll wind it up by 830. Okay. So expected value of summation 1 upon n variance of xi. All right. What will that be? Now, can I do this? Can I pull the summation outside and take the expectation inside? And each of these variances of xi, because they're random variables, the expected value will be the same. So I could say this upon n square. So if they're same, so the summation will go off, or rather, let me just for now keep the summation here. All right. And I can say expected value of variance of xi, right? And this is from 1 to n. All right. Let me use a different color to indicate separation between the two. Oops. Let's draw a line here to separate the two areas. Okay. Okay. Right. So now if I pick this up further, so it becomes 1 upon n square, and then so this expected value will come out to be some constant, right? So summation of 1 from 1 to n will make it n, right? And into, so what is that expected value? That'll be nothing but sigma square, right? Because that's the variance of xi. Now this expectation is over the population, right? So I get sigma square by n. Is this clear? So population will have this. So this mean, the random variable mean, sorry, the mean of a sample, right? Okay, we'll do that. We'll wind up by 8:15, right? The mean of, because anyways today's class is a little heavy, I guess. You will need to go through this because because if you understand this, whatever we are going to do today, this will take you a long way in using probabilities very well, or rather using this randomness concept very well. Okay, understand just the difference between sample and the population, right? So is this clear so far? What you have done? So what we can say here from this, what we can deduct is the variance of a mean decreases as n increases. What does that mean actually? So conceptually, what does that mean? You're saying variance of a mean decreases as x increases. It means, sorry, as n increases. What is n? N is my sample size, right? If my sample size becomes larger, we know this, right? That if the sample size is larger, and assuming that the samples that are drawn are independent of each other, randomly drawn, that means they will give a better accurate picture of the population. Yes or no? Agree on this? Larger the sample size, more accurate prediction of yeah, right? So so this whole thing is interesting this way, no? With when we understand the concepts rather than just mathematics. Mathematics without the concepts is boring. No? Okay. So as we saying that as the sample size becomes larger, my answer should be more accurate. If the answer has to be more accurate, means what? Anyways, the expected value is still the same. Whether I take a sample size which is 10 or 1000, expected value of the mean is the same, right? What is changing now? Though the expected value is the same, the spread can be different, right? So that is the whole concept of defining two degrees of freedom. One is the mean, another is standard deviation, right? So I'm saying but how much is the variance changing? So so that is so much more important, right? So this is what I'm saying. So we know this that so mathematically also, what is the equation behind that? How much does it decrease? So it decreases by, so variance decreases by sigma square upon n. So it's inversely proportional to the size of the sample. Is this clear now? All of you? Uh, Lavita, Supreet? Okay, good. All right, now this is another interesting thing. All right. So what is a standard error? Okay. So we say standard error is the standard deviation of sampling distribution of a static. Let's look at it as a definition and then we look at each of the individual parts here, right? Standard deviation is nothing but a mathematical computation. Okay, nothing more than that. What is a sampling distribution? It is the probability distribution of the given statistic based on a random sample. All right, we have to understand this also. So this is our static A, and based on that, what is the sampling distribution? It may be considered as the distribution of the static for all possible samples from the same population of a given size. So let me okay, so I'll come back to the definition. Okay, so I say population is a normal distribution with mean is mu and variance is sigma square. Let's say this is known to us, all right? And so population can have any large size, let's say a million, okay? And then say we take a random sample of some size n, let's say 100, okay? And then we take many such samples. So we take a sample of 100, we take another sample of 100, and we take many such samples. Let's take we take 1,000 samples, right? So we've taken 1,000 samples of 100 each, all right? And overall size is, let's say, billion, not even a million. So overall the population size is a billion. I'm taking 1,000 samples of size 100 each, okay? So now what is my static here? Statistic, right? So my statistic will be, in this case, in the arithmetic mean of each of these samples. So I've taken 1,000 samples. Each of these samples have 100 values. I take an average of that. Okay. Now, if I take an average of that, how many values will I have now? If I take an average of each of the samples, okay, and I said we were taking 1,000 samples. So how many values will I have? No, no, I will have only 1,000, right? Because whatever 100 values that I had, I summed it up, but I took an average of that. So each of those 100 gave me one value, right? So each of those 100 gave me one value and I'm left with 10,000 values, right? So these 1,000 values are what each of these are the uh, for each of those samples, I'm saying what is my average, right? So each sample has its own average value. The distribution of these averages is called the sampling distribution of the sample mean. Understand this. So those 1,000 values, now if I was to distribute that, if I was to plot that as a histogram, that would be the sampling distribution of the samples mean. Is this clear? So what is my definition of sampling distribution? Let me just show it to you. Or let's just do it in Excel, right? Let's look at this. I say uh, my data, all right? My raw data is equal to R norm 10,000. So I'm generating 10,000 random variables, all right? Uh, let me do it this slightly different. Okay. I say my M is population size, all right? So I say 10,000, all right? And then I generate those many random numbers, all right? Now what I want to do is these random numbers are there, okay? So now this is the, oops, can you guys hear me? So I'm generating a matrix. So why I'm generating a matrix? So I can have uh, some sample sizes, right? So let me say my sample size n is equal to 10, okay? So I say n is equal to 10, all right? Oops, I made a mistake. Okay, let me do that. We will wind then if you need to wind up, we'll do that today. Okay, let me just quickly finish this not mathematically, just conceptually. Is this okay? Huh? So if then we'll go through this in more details. So we're saying that we take a average. This now it is said that this will have a normal distribution of mu and sigma square by n. Know that the population had a normal distribution of n and mu comma sigma square. This will have a normal distribution which is mu and sigma square by n. Okay, so this we will look at it mathematically. We've already actually seen that in the previous case how it happened. Okay, and so now another static could be sample median, where instead of sample mean I'm taking sample median and I'm using the median to compute everything. Okay, uh, so I think we can then uh, stop here. I mean, another very interesting concept is that we will see what's the difference between standard error of a mean versus standard deviation. Normally we think they are the same. They're not the same, all right, and huge difference is there. Okay, I mean, if you have just learned things mathematically in your engineering, for sure you will think there is no difference. Okay, so we will look at those, and then we will kind of see that there is a bias that gets introduced, and we will go through some maths to understand that bias. Okay, uh, and then we'll go through further examples as we move ahead. I think then we stop here today. Let's just quickly summarize what we did today, because this is a very important concept. Okay, uh, so we're saying as far as variance is concerned, be very clear about the definition. Variance is the expected value uh, of the square deviation from the mean, all right? And so that is what it is. And then we saw that I can represent it as uh, so it boils down to expected value of x square minus ex expected value of x the whole square, right? So mean of square minus square of mean. Okay, so this is what it comes down to. And then we said, okay, let's look at the discrete random variables with in purview of variance. We say the variance uh, of a discrete random variable can be given by these two formulae here. One is 1 by n xi minus mu square, all right? That's just the variance. Actually, it's not the expected value. That I would say is the uh, uh, just the computation here, right? So when we apply the expected value here, so we look at some basic concepts of variance. So understand this. What we did here was not actually the expected value. It was just the computation, all right? Okay, so we did some computation, and then we will see when we apply the expected value how the values change. Okay, All right, so now we're saying variance has to be always greater than or equal to z. If there is a single variable, then they will not have any variance, right? And then we saw how we can apply linearity to variance. Okay, if there's a constant, that constant will get squared if I was to pull it out. Okay, and we generalized this concept, right? Once we generalized it, we further went ahead and we said, when there's if we are using random variables, right, from the concept of generalization, covariance becomes zero. And once that happens, and typically we will always be working on randomness, right? Because then only we can predict something. If there is no randomness, then it's difficult, right? That will be one basic assumption that we'll have. So we say the variance of sums is equal to the sum of variances, right? This is what we are able to compute, assuming that each of these random variables are independent of each other. Okay, and we also saw that by expanding this concept, we can say the variance of the mean decreases as n increases, right? Which is nothing but saying that the sample size should be bigger, right? And then we will say we will move ahead. This I think we will cover the next class. Is this okay? I think good enough. This much also is good because there was a lot to conceptually understand today. Okay. So guys, it will be good if you could also inspire others to come. I think I'm doing my best, whatever possible. I don't know why people would want to miss these classes, but anyways, their choice. I'll see if they can still get inspired to start coming to classes. But anyways, okay then. Uh, shall we stop here? Jai Gurudev.